Now we use such sequences to define stochastic integration of x with respect to m. That is not yet done. Till now what we have done, we have only defined what is integration of a simple process with respect to a square root equal contrast martingale, and the results, whatever it was isometry, whatever we have obtained, is also not general integrand, only for the integrand which is simple process. Now we are going to define stochastic integral for a progressively measurable process, which we denote as space of this L star of m. And after defining that, we are going to again ask the same question, whether that heteroasymmetry is still hold true there. So we are going to prove that again there. Of course, that proof would be different, because here in this proof we have heavily used that structure of the simple process, that it can be written as finite sum, etc. But there we cannot, correct? So we need to use the limit theorems, etc. So what is the idea? The idea behind defining the stochastic integral of x is that we have x in one side, x in one side, and xn is a sequence which is converging here, and then for every xn I can derive one ixn, and I can change n and check whether this ixn converges anywhere. If it converges, wherever it converges, that limit, I would call that as ix. So that is the idea. But for the as a first step, I should ask that whether that converges at all, or in other words, I would ask whether ixn is a Cauchy sequence. If it is a Cauchy, then it would converge, because it is in the space of MC2, which is a Banach space, closed subspace of M2. So now we take any m and n, and we would then let it go to infinity. For any fixed mn, first we look at ixn minus ixm. We consider this difference, and then this norm. So due to the linearity of I, we can write down I of xn minus xm, and then we are going to use the isometry property, which is established for the simple process, but here xn minus xm is also simple process, so I can use it. So this is equal to box norm of xn minus xm. However, the main thing here is that this xn is a sequence which converges to x, so this is itself a Cauchy sequence. So I would get this difference also goes to 0. The difference goes to 0. Since this goes to 0, therefore this goes to 0. And then what we have proved, that ixn is a Cauchy sequence. So we call that limit be z. So z is a limit. So what is z? Z is not a random variable, correct? Z is a stochastic process, because here our members are stochastic processes, correct? I have omitted, so whenever I do not write down any subscript t, that means it is the whole stochastic process. If I need to view only the stochastic process at a given time t, then I write down a subscript t there. So the limit is z. So z is in the space of continuous square root equal martingale, so that is the limit. Now the question is that this z is obtained via the sequence xn. A very natural question is that if I would have chosen another sequence, perhaps yn, which also converges to x, should I have got the same z or something different? If I would have gotten something different, then I cannot just then I am confused, correct? Then I will be confused which limit to be considered as the integration of x. What should be ix? Thankfully, we are going to show that we will be able to show that this z is independent of the choice of the sequence. It does not matter what sequence we choose which converges to x, always you are going to get the same z. So how to prove that? I mean, such type of theorem is generally proved by considering first as in the let there be two events, z and z prime, and then show that z and z primes are exactly the same. So we do the same way. So we show that z is independent of the to the choice of xn. So we assume another sequence of simple processes which converge to x in the box norm, and z prime is the limit of their integrals. So, limit of I y n. Then since x n and y n both converge to the same x, okay, that is our assumption. So, box norm of x n minus y n should go to 0. Okay. So, this go to 0. Okay. So, this much we have in our hand. So, now we consider the norm of the difference of these two integrals I x n minus I y n. Again we are going to use the Ito's isometry, what we have proved earlier for simple processes. So, that is again x n minus y n, but this goes to 0. So, this norm goes to 0, okay, as n goes to infinity. So, its limit and this limit should coincide. So, z and z primes, the difference of that is 0, okay, norm of difference is 0. That implies that z and z primes are indistinguishable. Why can we conclude that? Because already have proved that, okay, if they are indistinguishable, they are 0, and 0 that is indistinguishable. Okay. Now, next, so therefore, we are now good to use this z as the definition of the stochastic integral of x with respect to m. So, this is well defined. Okay. So, we use this I mean, so although we are using x n apparently, like we are choosing a particular sequence, but this integral is I mean the limit is independent of the choice of x n. Okay. So, I x, the integration of x, is defined to be integration of x n with respect to m. Okay. The whole process, okay, the process wise, okay, and then this limit is in the sense of the norm, okay, in that norm sense, is not pointwise or something, okay, in that that parallel norms for some x n converges to x in box norm. So, we write this integration, okay, this I x also in this manner. So, we use this symbol integration 0 to t I xs dms. We also denote this integration in this manner for I t x. And if I want to write down I x, then for that as an integration we often write integration 0 to dot, okay, xs dms, to denote that, okay, I am not integrating from 0 to say particular time, but is like is a stochastic process I just want to write down, which is arising from the integration. Okay, so these are the notations we might use in the future also. Now, now we consider. I mean, what I am going to prove is that the kind of Ito's isometry we have seen for simple processes. Now, for this integration, what is newly defined here, we are trying to prove that, okay, this also is an isometry. Okay. So, for that we again choose sequence x n from space of simple processes which converge to x in L star, okay, because our x is in L star, okay, and L star is closer is the closure of L naught. Okay. Then what do? We use Jensen's inequality for conditional expectation to argue that this integration of x n I t x n converges to I t x in L 2 p. Okay. L 2 p means that expectation of I t x n minus I t x whole square, that goes to 0. Okay. And then for any A which is in say sigma algebra of sth time sigma algebra, so Fs, we consider this conditional expectation, the expectation of I t x minus I x. This is the increment of the stochastic integral, square of the increment on the with the indicator function of A. That means that we are integrating only on the domain A. Okay. Expectation, the integrating in the sense not time integration, the space integration, the probability. So, probability with this polynomial when you integrate only on the set A. Why are you doing that? Because we are trying to prove certain measurable function to be something else. Okay, so like we are going to identify. So there is a this is a standard way to do that. So when you have a non-negative measurable function, say f and g, and if you can show that integration of f with respect to mu on a set A is same as integration of g with respect to same mu on the same set A is equal, does not matter whatever measurable set A you choose, then we can actually obtain that okay, f and g are equal almost everywhere. Okay, so we are going to use that. So here we are therefore using A to be fs measurable, and we are taking indicator function of A here. So now this expectation of the square is equal to limit n tends to infinity expectation of 1a multiplied itxn minus isxn whole square. How did I get it? Because this its and isx are the limits, and then this limit I have taken outside. Okay, so how could I do that? We can do because that of the very definition of their convergence. The definition of convergence is that itxn converges to itx in the parallel norm. In the parallel norm is like after taking expectation, and that thing converges there. So from the definition of the parallel norm, so we are going to get directly. So it is coming from the direct definition. Okay, because this it is not limit inside, because what I told in the beginning is not true, because this is exactly equals to this, that is it. Because the itx is not the pointwise almost sure limit of itxn. Okay, so itx is the L2 limit or the parallel I mean that norm limit of itxn. So this is coming directly, and now from here what we are going to do is that we are going to condition it. Okay, so what are the condition? I mean, so here time t and s appears, and a is also fs measurable. I want to get rid of a. Okay, so for that what I am going to do, I am going to take the sigma algebra fs. Okay, so we condition that itxn minus isxn whole square given fs, and then this indicator function of a comes out of this first integration, because the a is fs measurable, and then this I mean remaining term, using the result what is obtained earlier, it was isometry for simple processes. I can write down this one. Okay, I take this difference square, the square of this difference is integration s to t I xn u square dmu. Okay, so this part is obtained from the earlier result. So this thing, okay, from we are using this result here. Okay, so after using this result, we have a here again. So now this a I can put again inside, because this is fs measurable. Okay, so just to use that result, I took a one a outside, but now I am going to put it again inside. So when I would put it inside, it is not time dependent, u dependent, so it goes inside this integration also, and then square of indicator function is indicator function itself, so it even goes inside the square. So 1a into xn u. Okay, that process we are going to discuss. Okay, so for the time being, we actually we define this process. I mean this notation, we are using this notation. I mean this is exactly what we would get here, indicator function of a 1a times xn u. Okay, and u is more than s. Okay, so like this, and when u is less than s, which is irrelevant for our case anyway, so for that we are just putting it xn u. Okay, so this is another process we are going to consider. Now we are considering this process. Okay, this xn of into 1a this thing. Okay, this again remains to be a simple process. Why? Because I am just multiplying either 0 or 1. Okay, at places. Okay, so nothing would be affected, only xi I value would be affected. Sometimes it would be xi I as it is, sometimes it would become 0, say. Okay, if say omega is not in A, it would become 0. Okay, otherwise it is exactly the same. So that is the simple process we are constructing here. Okay, so why are we doing that? We are doing it so that to emphasize that we are still having simple process. So simple process multiplied with indicator function is still a simple process. And now we are rewriting this left hand side again. Okay, so this is just a rewriting, because this I can write down as again conditional expectation given fs. Okay, and then expectation outside, but then that expectation there taken for that conditional expectation, what I am going to get multiplied with indicator function of A. So that means integration of A with respect to the probability measure, the outside expectation would become this thing, and inside expectation, conditional expectation, what I am going to get is itx minus ix whole square given fs. So left hand side what is written here would be this thing. Okay, then right hand side, so I am writing right hand side now using this notation. Using this notation I am writing right hand side, the limit n tends to infinity x. So now this we understand that this is nothing but the box norm of this process, correct, because this 1a is here inside and then 0 to s to t this thing. So it is the box norm of I mean the difference of the box norm, because 0 to t and 0 to s and the difference. So this box norm of this thing. Okay, so limit n tends to infinity of this difference. Okay, so that thing we have obtained, and now we are again using that x, since xn converges to x. Okay, in that box norm xn multiplied by 1a would also converge to x. Okay, in the same box norm. Why? Because by multiplying 1a you have not changed anything fundamental, just some of the xi you multiply with this 1, the same thing, or 0. Okay, and that same thing remains, also you multiply to x also. So here it converges to x into 1a. Okay, yes.
How this indicator function is
Which one?
so this you denoted it with something.
This one. Okay,
So whenever u is less than this,
yes,
it is
x and u. Exactly. So then they are same, correct? So x and u. So now if you take the box norm definition, the box norm is,
to we try to push indicator function of a inside.
yes, exactly. So this indicator function went inside here.
We can only push when a is measurable with respect to
Fs, of course, A is measurable to this Fs. A is in Fs. That is the whole point.
then it should be in both cases.
Exactly. So A was here, and then I have taken out here just to apply the Ito's isometry formula for simple processes, and then after obtaining this using that formula, again my job is done. Then I would put 1a inside, correct? Okay, so when I put it inside, then the new simple process is 1a dot xn u, and that is here denoted, the notation is properly explained here. I don't care what happens before s, since I don't care much, I just put it same as xn u. Okay, and for u more than s only this is relevant here. So for that I define this multiplication, whatever I want. I mean, the reason that I have here, I have kept it here because that I want to retain the measurability issue. You understand? If I multiply C still 1a here, then it does not remain simple process, because this is Fs measurable, this is EU, and then the definition of simple process is violated. Okay. So that is the reason. So now it is simple process. Now xn 1a is a simple process, and I can therefore use this use this convergence, that xn converges to x in box norm. So xn into 1a, so this process also converges to x into 1a. Okay. So now after this convergence is done, so it is now time to rewriting this I mean here I think small t is missing, so subscript small t is missing, and then is equal to expectation of this 1a of x square u dmu. So how did I get it? Because again I'm writing down this as integration of the like above, and then again we have taken 1a outside and then we have obtained that. Okay, so 1a x square u dmu with respect to this quadratic variation, okay, x squared u. So now here this thing I can write down as that this outside, I mean I can put one conditional expectation here, condition with respect condition with given the fs, okay, sigma algebra. So when you do that, then outside expectation becomes just integration with respect to probability measure on a set A, and inside the conditional expectation what I am going to insert would be expectation s to t xu square dmu given fs. Okay. So using the tower property, so here we have inserted one conditional expectation here, and that is survived here, and the outside expectation becomes this integration with respect to p on the set A. So at the end what did I get? I got this equality for all A which is fs measurable. So integration of this non-negative measurable function, okay, it is fs measurable function, correct, fs measurable random variable, with respect to probability measure on a set A is same as, this is also non-negative square is there, expected conditional expectation of this thing, or this whole thing is fs measurable. So expect integration of this non-negative random variable on the same set A which is the same measure p. So they are equal for all A in fs. What can you conclude now? We can conclude that these integrands are same. Okay. So in the next slide we write down that expectation of itx minus isx whole square, so square of the difference of the integrand is equal to expectation of the integration of the square of the integrand with respect to the quadratic variation given fs. Okay. Now we can put s is equal to 0 and we take expectation, and then we are, so this part vanishes, we are going to get this thing. Okay. Again this is saying that norm of ix, okay, it does not directly say that. So we have to put t is equal to n, and we have to just write down this for all possible n. This is true, and right hand side is just this small, it should be capital M, okay, it's a typo, and this right hand side is the box norm at t, okay, at n. So t is equal to n we are going to put, and then they are equal for all n. So now you take 2 to divide by 2 to the n and sum over all possible n to obtain that, okay, norm of ix is equal to box norm of x. Okay. So that is true, we have obtained this for all possible x in instar n. So what did we prove? We have proved that isometry, that I is an isometry also from the space L star of m to m to c. Okay, L star of m is on the one side where x is coming from, and ix is going to mc2, the square integral continuous martingales, and this I map is an isometry, it preserves the norm.